Thank you, Andre. So this is the third talk in this mini-series, but this one is actually reasonably independent from the previous two, except that I kind of assume definition of Markov chains. So what is going to be about? It's going to be about the conductance, canonical paths, and I'll say a little bit about canonical flows as techniques for proving bounds on the mixing time. And we have other techniques like comparison, decomposition, and several others, but I'm going to focus on these, partly because my theme for the day is Markov chains on matchings, whether all matchings or perfect matchings. And canonical paths is pretty much the only thing that we've managed to get to work on these to get reasonable bounds. Just like what Leslie did and Lenka, I'm listing a lot of people here to thank for contributions that I'm going to talk about. This is kind of like an error correction because I'm trying to also list the references on the slides, but in case I forget anybody, I apologize. Okay, so what's going on here? I'm going to assume throughout today's talk that my Markov chain is ergodic. That means that I have a unique stationary distribution. And just to refresh your memory, ergodic means that it's aperiodic and it's also irreducible, meaning I can go from everybody to everybody. And moreover, I will mostly assume, actually I think I will assume throughout the talk, that my Markov chain is also reversible, so I can go back and forth between my states. Now my picture here, these bubbles are my states. I have transitions. I'm not telling you what the probabilities are, but it looks something like this. Now, when does the Markov chain mixes? We saw, and I gave this beautiful talk yesterday about using the coupling technique. But now let's kind of just look at this graph and try to understand combinatorially what's going on. So here it seems like if we take a walk in this kind of scenario, this is my transition graph, we feel reasonably confident that we could mix. On the other hand, if my transition graph looks like this, especially if my left set is kind of exponentially large and so is my right set, and I have this teeny tiny connection between them, then even if I were able to kind of mix in one side, then it would take me, and if this is exponentially large part, then it would take me exponentially many tries to even get to this one state to be able to even move to the other part of the state space. And so this is intuitively not going to mix. And this brings us to this definition of conductance. In other words, it also goes by Chigger constant. And what it is, it's essentially the escape probability. Okay? So for computer scientists, this is kind of like a cut in a graph. So I'm going to look at all possible subsets of my states. And technicality, I'm going to look at only at subsets that are in probability distribution mass smaller than 1/2. And then I'm going to look at a state inside my set, that's probability of being in the state, and then probability of actually escaping outside, going to a state Y that is out of S. And I'm normalizing it by the mass of S, so essentially conditioned on being in S, pi of X over pi of all of the states in the set S is going to be the probability of X conditioned on being in the set S. So let's see what I mean. In my graph here, excuse me, suppose that I have my stationary distribution uniform, meaning all of my states are equally likely. And this is my S, so I have 3 states. The probability of S is 3 over 11, smaller than 1/2. And these edges are the escape edges, and now I'm telling you what the probabilities are. And so now, when I go through this calculation, I get a beautiful expression, something like that. And now my conductance for this specific S is 0.3 here. Okay? If I look at this one, I get 0.02, so it's much smaller. Now, what does this really tell me? Well, I'm not going to prove this theorem, but it's possible to relate the conductance to the spectral gap. Okay? And not just relate, it's possible to use conductance to upper bound and lower bound the spectral gap. There is a small difference. The upper bound is a linear function of the conductance. The lower bound is a quadratic function. And why does this matter? Well, this is something that we saw in the first talk. The spectral gap gives me a bound, an upper and a lower bound on the mixing time. Okay? So now I'm going to rephrase this theorem. I'm going to simplify it a little bit, putting the conductance in. And assuming laziness, the theorem can be now simplified to getting an upper bound and a lower bound on the mixing time in terms of the conductance. Okay? So the goal is, if we can bound the conductance, if we bound it from above, we are providing a lower bound on the mixing time. If we bound it from below, we are providing an upper bound on the mixing time. Okay, well, that's nice. But now the question is, so what we want, let's go back. What we really want, we want to provide usually an upper bound on the mixing time, so a lower bound on the conductance. That's kind of nice, but, well, sort of. So what happens is, if we want to provide an upper bound on the conductance, it's enough to just look at a bad set S and compute its little escape probability, the Q of S. But if I want to provide a lower bound, that will give me an upper bound on the mixing time. Well, in that case, I kind of have to look at all possible S's and find the minimum. Okay? So how do we go about that? And this is where the brilliant idea of Jerram and Sinclair comes in, and that's called the canonical paths. So what happens, again, computer scientists, when we hear a cut, what is the first thing that comes to our mind? A flow, right? Min cut equals max flow. Well, the world is not as beautiful here. We will not have an equality, but we will have a relation. So Jerram and Sinclair came up with this idea of setting up a path in the transition graph between every pair of states. So for every pair of states, now I'm going to call them I for initial and F for final. So here, if I take my I and F over there, I'm setting up, let's say, this path. Then I have another one, IF, another one. I sort of gave up here, but in reality, there's a lot of paths here. Okay? There's as many as the number of states squared. Okay? So now, what does this really do? Well, in a way, the conductance is telling me how much probability mass I can get from a set S to outside. And now canonical paths, if I am going to send a good amount of kind of volume of stuff from I to F, then I will know that I will be upper bounded by the conductance, and therefore the canonical paths will provide a lower bound on the conductance. Okay, so now how does that really work? Well, let's take a set S. Okay, now I'm going to look at the probability mass of S, which I should have mentioned before. It's just sum across every element in S, every state, and its probability. And if I take the probability mass of S and multiply it by the probability mass of the complement of S, well, then what I'm really getting is, this is just a simple summation, I'm summing across everybody in S and everybody outside, and the probability of the state in S times the probability of the state outside. This is just a definition. Okay, I mean, it comes directly from the definition of what pi of S is. Now, the only thing I've done here is I divided by the escape probability when going from S to the outside. Okay? So now, let's look at the left-hand side. Now my left-hand side is lower bounded by, I'm going to take S to be the smaller of the two, S and S complement. I have a reversible chain, so it doesn't really matter. And therefore, this quantity, the complement, is lower bounded by 1/2, so I can simply write this expression. But this expression is something that we have seen. It's really just a definition of the conductance, the reciprocal of that, and half. But it's a definition assuming that now I'm actually looking at the smallest possible cut S. Okay? So that's my left-hand side. Now let's see what happens with the right-hand side. With the right-hand side, Now, I can express this fraction as, instead of summing across all initial final pairs, one in, one out, I can look at every single little edge that brings me outside state inside as going directly by a single transition to a state outside. That's my x and y. And then I look at all of the paths that go through this specific edge. Okay, so the picture is, here's my xy edge, and then I have all these wonderful paths that go through there. Okay, that's this summation. I know it's a gorgeous expression. And now the bottom is just the same. And now with a simple averaging argument, if I give you a set of n numbers and I take the average, we know immediately there's going to be one number that is going to be bigger than the average, or at least as big, right? So the same kind of an idea applies here. I'm going to now take the ratio of just the inner parts of these two summations. I'm just going to take the ratio of this and this component, and by the averaging argument, I know that there's going to be an xy pair, xy, such that this ratio is bigger than equal to the average. So this is what I get. Now, this is actually the end of a proof. We will see what we just proved. We proved that 1 over the conductance times a factor of a half is upper bounded by this quantity. Now, what is this quantity? This quantity is, there is some transition going from state U to state V. Okay, here's the transition. There's a bunch of paths going through it. They just go, go, go. And each of these paths is taking, contributing a volume of pi I times pi f. Okay? We are summing all these volumes, and then we are dividing it by the kind of a capacity of the edge. Okay? And we will, I just took the expression up here. This is what we got. And we can call this as the congestion through this transition UV. Okay? So now what happens is, simply taking this, we have an upper bound on 1 over conductance, and that immediately from the previous theorem that I showed you gives me a bound on the spectral gap, and I have a bound on the running time, on the mixing time. Okay? Now, this analysis, because of the relation of the conductance and mixing time being kind of like a square, this can be actually improved. So I'm not going to use this definition of congestion. I'm going to use a slightly improved definition of congestion due to Alistair Sinclair. And it's kind of the same thing that we had before. I am looking at a transition UV. I'm looking at all of the paths that go through it. The paths contribute pi of the starting point of the path times pi of the end point of the path. But now I have this additional length of the path, but the actual mixing time bound will not be a square of this value, but it's going to be just a linear function of this value. Now, one last thing that I forgot to mention, well, I don't really know what U and V are. So instead of figuring it out, I'm just going to maximize, and essentially, in words, what this boils down to is I'm going to look at the most congested edge. If the most congested edge is not very congested, then I have rapid mixing. Oh, I forgot to mention, rapid mixing in this context means polynomial mixing. Okay? Okay, so an example is coming, but before that, here's the theorem. If we bound this wonderful quantity called congestion, well then, a mixing time bound that we get is just 4 times this value, the congestion, times logarithm of 1 over epsilon times the smallest stationary probability. Okay, so that's the framework. Now, an example is coming. So let's revisit matchings. I defined matchings last time, but in case there is somebody who wasn't here before, a matching is I have a graph, I have a set of edges that are vertex disjoint, and a matching is called perfect if all of the vertices have an adjacent matching edge. So and last time we talked about if we know how to sample matchings, we know how to approximately count them. Okay? So the goal that we want to do now is to just figure out how to sample matchings. Now, how to sample matchings? Well, let's set up a Markov chain. And here is the Markov chain. So my state space is all possible matchings. And I'm going to do the following. I'm at a matching, and I choose a random edge. Now, something like this. If my edge is in the matching, I remove it. If my edge, on the other hand, was not in the matching and it's not adjacent to any other matching edge, I add it in. Okay, now it's in. And now again, next step, I choose a random edge. Oh, this random edge has one endpoint covered by a matching edge and the other endpoint not covered. So what I can do, I can kind of slide this edge over here. Okay, and I refer to this chain as the sliding chain. And so we can kind of keep doing this for a while. And as a technicality, I'm going to make this chain lazy, so every other, I'm going to make a step only with a probability 1/2. Okay? That's just for the theorem to be applicable. Okay, so now the framework that we had was find a path from any state to any other state so that we don't have a very congested transition. Okay? So what happens here is our states are matchings. So I'm trying to go from matching 1 to matching 2, here from red to blue, okay, without creating a very congested state. So the very first thing that I could try is to start in the matching I and remove all of the edges, okay. When I say a path, I get to use a transition at a time, okay. So I can start with my red matching, remove my first red edge, then the second red edge, and so on and so forth, and I get to the empty matching, right? And then I can go and keep adding the blue edges. All of these things that I'm describing are valid transitions of my Markov chain, right? So now, this is a canonical path, but it's not very good, because the empty matching is super congested. Everybody goes there, right? So I'm trying to avoid this. So instead, as Jingi told us, when we see two matchings, what are we supposed to do? Well, we put them together, and we get a set of alternating cycles and alternating paths. So I have these even length cycles, red, blue, red, blue, red, blue. I just took the symmetric difference. And now, what I can do, I see these wonderful cycles and paths, and I order them. What do I mean by ordering them? Well, the vertices have some labels. Let's call these labels 1 all the way to n. Okay? So the vertex that has this, the component, the alternating cycle or path that has the smallest label vertex is going to be my first component. Then from the remaining components, whoever has the smallest label vertex is going to be my second component, and so on and so forth. So I have some canonical way how to order my components. And now I'm just going to process these components in this order. So I look at my first component, and, well, what does it mean to process? We want it to go from red to blue, right? So I have, the notation that I'm using here is the straight edges, the non-dashed edges, are edges that are in my current transition, okay? And the dotted ones are the ones that are not, but I kind of want to have them in. I'll come back to that soon. So now, I'm processing the very first component. I know the lowest label vertex. That's my vertex 1 over here. And it has this red edge, and I don't want it. So I take it out. And then, what that allows me to do, it allows me to slide the next red edge into the blue, and I go. And then the next red edge into the blue, and I just keep around the cycle. And the very last edge, I just need to put it in. Okay? So I process the very first component. So now it's not true anymore that my dashed edges are the edges that okay, so what's happening now, my dashed edges are edges that either I still want to get in or I've already processed and I don't care about them anymore. Okay? Okay, so now let's go to the second component. If my component is a path, I don't start with the lowest vertex, but I start with an endpoint, and I kind of keep going flip, flip, flip until I change red to blue. Okay, now my path here is kind of teeny tiny, so what it really means is I just slide my red edge to this blue, okay, and I still need to, so if my path were longer, I would keep sliding, sliding, sliding until the very last edge, if I need it, I add it in, okay. Now I do the same thing with my third component, and I go like this. So the beautiful thing that happened was that I actually haven't used any of the other edges except for the edges in my matchings. And at any given time, I was kind of close to one or the other of the matchings. Okay, so I'm going to now try to formalize this. Oh, but before that, I know you really like this expression for the congestion, so let's look at it again. So now, what really happens is, what we want to figure out how many of my alternating cycle flipping paths go through any given transition. Okay? But now, I am actually at a symmetric chain. If I slide, I can slide back. If I add an edge, I can remove it, and vice versa. So my stationary distribution is uniform, meaning the probability of any matching is 1 over the total number of matchings, which simplifies this wonderful congestion expression quite a bit, because 1 over pi of I, pi of f are each 1 over omega, pi of m is the same. So when we cancel things out, what we really are left with is just 1 over omega. Then we have 2m for the probability of the transition, because we're choosing a random edge and we're doing it lazily. And then we have the length of the path. And the length of the path, well, how many transitions do we need to go from red to blue? Well, we're just going through the edges in the matching. And so the number of the length of the path, the number of transitions I need to go from red to blue, is upper bounded by the number of matching edges, and so that's n. Okay, but now if we look at this simplified bound, well, what really happens is n comes to the 2mn over the size of omega, meaning over the number of matchings. And this summation now just boils down to the number of canonical paths through my transition. Okay, so what I want to bound is the number of canonical paths through my transition, and in particular, I want to bound it by the number of states, and possibly times a polynomial factor. If you think about how many canonical paths I have all possible starting states, all possible final states, so I have number of states square canonical paths, right? And I want only number of states canonical paths to go through my transition. Okay, so let's see what happens. Here's my transition, okay? It coincidentally happens to be a transition that we've seen in my little demo. And just to reinforce it, what we want to show that the number of paths, number of pairs of red and blue matchings that go through my beautiful, wonderful purple transition is going to be bounded by the total number of matchings. Okay? So essentially what happens, this is a purely combinatorial argument now. We are going to show that's the case, and let me show you when did we see this transition. We saw it when we've already processed the first component, we were processing the little path. Okay? So in reality, I'm going to now reveal the colors of these edges. Obviously, my transition doesn't know who is blue, who is red. It's just a happy matching that is being shifted to another happy matching. But we do know who is who. And we knew that the situation looked like this, okay? So now, let's look at the complement of the transition with respect to the original and the final matching, okay? In other words, I look at, well, in my case, I don't really have any common edges. I'm just looking at the union of I and F, union of red and blue, and I look at the edges of the transition, took that out, and what am I left with? I'm left with my dashed edges, which are forming a matching, right? Okay. So, and this is another brilliant idea, actually, how to use canonical paths. This matching, this I union F, the start matching, the end matching, minus the transition, let's call that an encoding. Now, in what sense is it an encoding? Okay, let me highlight this. So I have this orange encoding. Well, I kind of want to say that it encodes the path that we got it from. Okay? So the situation that we have now is I know the transition that I'm trying to figure out how many paths go through that transition. That's my purple. Now, somebody gives me this orange and says, well, if I give you this orange, that you know there is one path that kind of corresponds to this purple/orange combo. And so this orange information would encode that path. Okay? So the question is, can we now look at purple and orange and figure out who used to be red and who used to be blue? Okay? And it's actually not too difficult to reconstruct I and F, because look at the cycles and the path. Those are exactly the same cycle and path, exactly the same components that we had before. The components themselves do not depend on who is colored red or blue. So we know the components, and now we know that we are making a transition in the second component. That means that the first one must have been already done. And since the first one must have been already done, that means that the edges that are in the transition have been already switched to the final matching, to the blue one. And the edges that are in the encoding, the other ones, have been taken out. So they used to be red. Okay? Now, we can do the same thing for the third component because we know it's coming after the one that we are processing. So now the purple, the transition edges, haven't been taken out of the red yet, so they have to be red, and the other ones are the blue ones. Okay? And now the final thought is what happens with the component that I'm currently processing. And there we know what has been done before the transition that I'm looking at, what still needs to be done, and based on that I determine who is supposed to be red and who is supposed to be blue. Okay? So the bottom line is we were able to reconstruct this situation. So from the encoding, from just somebody comes and gives me a matching, and from that I can figure out the two matchings that I'm moving between, and I'm going across the current transition. Okay? So what that means is, I think I had a slide on that. So what this means is that the number of matchings through my transition is, let me say it again, the number of paths through my transition is bounded by the number of matchings, right? Every path is encoded by a matching. And therefore, what we wanted was to upper bound the number of paths through a transition by the number of matchings, possibly times a polynomial factor, and we did that. Okay? Okay, so, well, except that I kind of didn't quite tell the truth, because there is one other case that I just want to very briefly point out. What if, still the same transition, but now we would be actually dealing with the following red and blue pair? So now the components look differently, right? For different red-blue pairs, the components look differently, even though we're going through the same transition. Okay? So now if we try to encode this red and blue pair, we still look at who is first, who is second component. We get the encoding as taking the union or symmetric difference of the red and blue. We remove the purple edges, the transition, and we are left with this orange. But now, is this a matching? Well, not quite. It's almost a matching, except for this one vertex, because it just so happens that I'm processing a cycle. And if we are kind of flipping a cycle, there is this one case where we have two edges that are not in. But there is a very simple solution. We can simply remove one of the edges, make this into a matching. So now I have the orange matching, and now I claim that this is good enough, because what I can do, if somebody just gives me the yellow or orange, the encoding in this case, well, I can look at my components. I can figure out who is first, who is second. I can figure out who is blue and who is red in the prior component. I can figure out who is blue or red in my current component. But there's one minor, teeny tiny detail, which is I do not know whether my current component is a path or whether it was a cycle and I removed that one edge. Okay? So I don't know whether it was this scenario or this scenario, but it's actually very easy because I just remember one extra bit in my encoding. Okay? So what it comes to, instead of encoding, I just remember 0 or 1, and so then instead of bounding the number of paths by the total number of matchings, now I bound it by twice the number of matchings. Okay? So the take-home point here is when we want to use canonical paths, we're trying to find a way how to move from one state to another state without congesting any of the transitions. And what does it mean? Well, if we are in the uniform distribution, this criterion really means the number of paths through any given transition is supposed to be bounded by the number of states times possibly a polynomial factor. And how do we bound the number of paths by the number of states? Well, we kind of want to take a path and encode it into a state. Okay? Okay. So now, that being said, what we got for the sliding transition, we got the upper bound on the number of canonical paths as twice the number of states. We still need to analyze two other transitions. One is the add transition, and the other one is the remove transition, but I'm not going to do those, but we can do it the same way. And so what it boils down to is a bound on the congestion of roughly 4 times mn, if I didn't make a mistake. And that gives us a bound on the mixing time. And that, in turn, gives us an FPROS, a randomized approximation scheme, using the product of the ratios that we discussed last time. Okay, well, now let's move to perfect matchings. So what happens here, the Markov chain is very similar, except it's now not going to move on the state space of all matchings, but it's going to stay within the state space of perfect matchings, but it's kind of hard to move from one perfect matching to another perfect matching. So instead, it's going to go through all perfect and near perfect matchings. Okay? And near perfect means that I have exactly 2 vertices that don't have a matching edge. So they're kind of like the holes. Okay, so what it does, here I have a perfect matching. Now I am going to choose a random vertex. It's just a small modification to speed up the chain, to decrease the probability of the transition. So I'm choosing a random vertex. If it's adjacent to a matching edge, I take it out. Now, and that introduces 2 holes, 2 uncovered vertices. And now I, again, choose a random vertex. And I choose one of the holes. And now, if the vertex has a matching edge, I get to slide it to the hole, provided that there is actually an edge between my chosen vertex and the hole that I chose. So in that case, I slide, otherwise I don't do anything. And if I happen to choose a random vertex which is equal to my hole, and there is an edge between the 2 holes, I add that edge to my matching. Okay, so very similar chain, except that now I have these two holes that are kind of moving around, and sometimes I add an edge between them. Okay, so the analysis of this Markov chain is very similar to the previous one. The canonical paths are kind of the same, with one small exception, which is, well, if we have a path between a perfect matching and a perfect matching, Jean told us that if we take two perfect matchings, we have wonderful alternating cycles, and we just do it exactly the same way as before. If I'm going from a near matching to a perfect matching, then the picture looks something like this. I have alternating cycles and one alternating path. And now I kind of need to process the alternating path at the very end, because otherwise I would be introducing another holes, not during the time when I'm processing, when I'm moving from my red to blue, but when I'm doing the encoding part. Okay? I'll show you what I mean. So I have the components, and I do the flip, flip, flip. I would have fixed the first component, and maybe I would have fixed the second. Now, this is not what I'm going to do. I'm just kind of showing you what would have happened if I process the path before a cycle. And now I'm processing a cycle. So I need to flip cycle number 3, component number 3, from red to blue. And so what happens is I would have the purple transition. And when I look at the encoding, I would have the yellow encoding when looking at red and blue taking purple out, so I'm left with orange. And now we see that we have 1, 2, 3, 4 holes. So the encoding would not be in the state space that I'm working with, because I'm working with only perfect and near perfect matchings. So I wouldn't be able to use this to bound the number of paths by the number of states in this way. Okay? But if I process the path last, it doesn't happen, and I'm fine. Now there's one other technicality. What happens when I go from near to near? Then I kind of don't really get to avoid this issue. I would have had the 4 holes no matter what. But the solution is not to even try. So what that means is, instead of even defining these paths, so here are my near matchings, and here are my perfects. And we know, take your favorite near matching, take your favorite perfect, we know how to go from near to perfect, right? So now I want to go from my near matching number 1 to my near matching number 2. So I'm going to go to a perfect matching, the way I know how to do it, and then from the perfect to the other near. Again, I know how to do that. But how do I choose this perfect? Well, you can kind of think of it as randomizing across all of these perfects. But now this is the time when I'm going to introduce this idea of a canonical flow instead of a canonical path. So a canonical path is supposed to be a path from an initial state to a final state. But I don't really need it to be a path for the arguments to go through. This path is completely okay if it splits, as long as the total mass that it sends from the initial to the final is pi I times pi f. Okay? And so with this same logic, and all the theorems and everything goes through, so with the same logic, what I can do is, when I go from near 1 to near 2, I kind of split myself to go through all possible perfect matchings with equal portion, and then I come back to the other near matching. And what this boils down to is that my running time now gets multiplied by a fraction of the number of near matchings over the number of perfect matchings, because that's the contribution of the additional by going through the perfects. Okay, so this is nice if we can bound this number of near perfect matchings to perfect matchings by a polynomial factor. Then we have a polynomial algorithm for sampling. Well, for sampling what? That's a good question. Well, what if my graph, my input instance looks like this? Well, how many perfect matchings are there? Like 1. because the endpoints have to be, and it just goes that there's just one perfect matching. But how many near perfect matchings are there? Well, if I leave the endpoints unmatched, then I have exponentially many near matchings. Every one of my little boxes has two choices. So even if I were able to improve the analysis on the mixing time, if my goal is to be able to sample perfect matchings, this wouldn't have helped. Because it's like I have one thing that I'm trying to find randomly in exponentially many other things. It's kind of like looking for a needle in a haystack. I just wouldn't be able to do it. The good news is that there are some graphs for which the number of near matchings and perfect matchings, the ratio of these two, is bounded by a polynomial factor, by polynomial function. And, for example, the dense graphs would be such a class of graphs. Okay, so, well, let's try another Markov chain. So this Markov chain is only going to work on perfect matchings. Okay, so now I'm getting rid of the near issue, no near matchings, just perfect matchings. And this is the so-called swap chain, sometimes credited to Diagonis and Gangali, in a different context, in the context of contingency tables. So the swap chain, what does it do? Well, choose two random edges, like these two. I am choosing them, giving them the vertices names, because based on which vertex is chosen as the first and which as the second, that's how I'm going to do the swap that I'm about to describe. So now, choose two random edges and swap, okay, like this. And, well, you might immediately suspect that there is something funny going on. Well, if I choose these two random edges, I can't do the swap, so I don't. That's fine. That's kind of like a little self loop, staying within the same state. But still, there is a bit of an issue. If my input graph looks like this, I can't really move. There is no way how to get to the other perfect matching. But let's look at if my input graph, on the other hand, looks like this one, then you can verify that there is actually a way how to go from any perfect matching to any other perfect matching. Okay, so does this Markov chain mix rapidly? Do we have a polynomial time mixing time bound on this Markov chain, provided that we have an input instance on which we can actually go to all of the states? Okay, well, maybe not. So look at this instance, kind of inspired by the example that we saw before. We have the chain of boxes as what we had before, and then we have one other edge connected in this specific way. And now, if I match the bottom two vertices to each other, I have only one way what to do with the top, right? Now, if, on the other hand, I do not match the bottom two vertices to each other, I match them to somebody up there, then I have only one possibility of how to do the matching edges on the left of this left edge connected to the bottom vertex. But I have many possibilities between the two, let's call it horizontal, vertical lines. Okay, so now I claim that I can actually go from any matching on the left to the matching on the right, and it kind of just, you can verify it very quickly that you can do that. So now I have a connected Markov chain. I have an irreducible instance. Okay, but the number of matchings on the left is exponential. The number of matchings on the right, there is just one that matches the bottom two vertices. Okay, so I'm going to use this as sort of a gadget, if I may, sort of a gadget to actually show that this swap Markov chain doesn't always mix in polynomial time. Okay, in this case, the case that I'm just showing you, where I took the previous graph and I repeated it 4 times in this kind of in this configuration, the swap chain does not mix rapidly. It actually needs exponentially many steps to get to the stationary distribution for this instance. And how does that work? And this is the reason I wanted to go through this example. We get to use the conductance to actually provide a lower bound on the mixing time. Okay? So the game that we are playing is, here's the definition of the conductance on the left over here. We can easily notice, just by the analysis that we saw before, that if I look at matchings that look like my left scenario, where I look at the 4 middle vertices and they're matched to the left and the right part, which forces matching in the top and in the bottom. Okay? And I have exponentially many possibilities on the left and right. So there's exponentially many matchings of the left kind. The same argument holds for the right kind. Now I have the 4 middle vertices and they're matched to the bottom and top, which forces the matching on the left and right, and I have exponentially many such matchings. But the way to move from left to right is to get the 4 vertices matched to each other and then flip them, and that's how we get to the right. So really, if I kind of look at the geometric properties of my transition graph, I have exponentially many guys on the left, exponentially many guys on the right, and just one connection between them. And so when I look at that connection, which corresponds to exactly this set for the conductance, I get this expression, and so there's only one edge that gets me out of S, which is flipping these 2 edges this way, and so I get an exponential upper bound, well, exponentially small upper bound on the conductance, which gives me an exponential lower bound on the mixing time. Okay? Okay, so now the last part of the talk. The example that I took here, there is this related problem called contingency tables and binary contingency tables. I took this example from a paper with Nayantara and Dana Randall, but if you want to learn more about the swap chain and in which scenarios it's going to work, there is a very nice recent paper by Dyer, Jerome, and Miller. Okay, so now the last part of the talk is talking about the permanent. Okay, so just to remind you, the permanent is like the determinant, but before got the -1 part. So, and I'm not going to actually get into this definition, but if you think about it, if A is your adjacency matrix, you're just going to count the number of perfect matchings in a bipartite graph. Okay, so that's what I'm going for. Try to figure out how many perfect matchings are there in a bipartite graph. If you recall, we know how to count all of the matchings approximately. That's what we did in the first part of the talk. Okay, so the trouble is that my favorite chain of boxes instance is bipartite, right? So even if we could improve the mixing time analysis of the sliding chain that we had before, we would have this picture, just like what I said before, but now I'm showing it pictorially, right? We discussed we have one perfect matching, that's my blue portion over here, and we have exponentially many other guys. Well, we don't like that. But okay, let's analyze the situation a little bit further. Oh, what happened? Oh, okay. So the idea of Jerome, Sinclair, and Vigoda is to change this picture. Okay? So we see how that works. So if we analyze the situation a little bit further, so the blue ones are the perfect matchings, and then we have all of these matchings with a specific pair of uncovered vertices, okay, with holes U and V. Okay? So this is my holes at U and V, this is another pair of holes, and so on and so forth. So I have n squared for the number of holes plus 1 different regions. 1 is for the perfect matchings. Well, I don't like this picture. My blue one that I really want is exponentially small, but I like this picture. I kind of want to reweight the picture so that I do not have my regions of so different sizes, but I want them to be roughly equal. Okay? If I know how to do this, then, well, I will simply sample from this state space, and with probability roughly 1 over n squared, I'm going to see a perfect matching, right? Okay, so what I want is every matching before I had a uniform stationary distribution. Now I want to adjust the proportion for a near matching. If I have a near matching with holes at U and V, I want to adjust the stationary probability by the weight of number of perfect matchings over the number of near matchings. And if we now think about the calculation, what we get, it would have changed the picture this way. Okay. Now, well, there's only one problem. We started from the problem of trying to count the number of perfect matchings, and now we're trying to figure out the weights of number of perfect matchings over the number of near perfect matchings with holes at U and V. So it seems like from a bad problem we went to a yet even more difficult problem, right? But don't despair. There is, this is all Jerome Sinclair Vigoda's idea. There is a way how to go about this. So if my target graph looks like this, okay, it's a bipartite graph, but actually it doesn't really have to be for this picture. But I have a target graph, and I do not know how to compute these weights. Well, let's simplify, as Florian told us yesterday. So if we start with an easy graph, okay, we know how to compute the ratio. We know how to compute the number of perfect matchings over the number of near matchings with holes at U and V, right? Okay, we'll actually, let me see if I have it here. What happened? Whoa. Oh dear. Oh, okay. That was supposed to happen. Okay, so we will start with an easy graph, like the complete graph. I'll show you what the computation of the weights is in a second. And then we will gradually remove the edges that we don't want, okay, until we get to a graph that we like. So if we start with an easy graph, the complete graph, we know that the number of perfect matchings over the number of near matchings is n factorial. Now this is the time when I'm using bipartite, though I don't really have to for this, but let's do that. So I get n factorial for the number of perfect matchings in the bipartite graph, okay, over number of n minus 1 factorial. Now, what I'm going to do here, I'm going to add weights to the edges. The edges in the target graph are going to stay at weight of 1. But the edges that you almost don't see, the ones that I kind of gradually removed, I'm going to give them this activity, or for our physics friends, the kind of a temperature analog that is going to start at 1, and then it's going to get decreased and decreased and decreased until we fade it away. Okay? This is very reminiscent of the annealing process. We start at a high temperature, and then as we cool down, well, high temperature is supposed to be like messy but easy, and as we cool down, we get to the state that we want to be at. Okay? So now, what happens is with the lambda in, instead of doing the number of perfect matchings over number of near matchings, now I'm doing the lambda weighted variant of this. Okay, so what this means is I'm always going to work with the complete bipartite graph, but now some edges will contribute this lambda factor. So once my lambda factor gets teeny tiny, it's almost as if the matching that uses a lambda edge didn't exist. Okay, I should have told you what the weight of a matching is. It's just product of these weights, either ones or the lambdas. Okay. Okay, and so now with this understanding, we have an estimate on the ratio that we want for lambda equal to 1. And now we can use sampling, well, actually, even before that. And then what we can do is we can keep the following invariant. We will start with lambda equal to 1. We know the weights, and then we will keep decreasing lambda. And the invariant that we will keep is that at any given time, we will have a 4 approximation of the weights for my current lambda. Then I will use sampling for this lambda to improve the approximation factor from 4 to 2, let's say. And that allows me to decrease my lambda a little bit. And what used to be a 2 approximation factor is now the 4 approximation factor for my new lambda. At a high level, does this make sense? So 4 approximation, boosted using sampling to 2 approximation, and then decrease lambda, what used to be a 2 approximation is 4 approximation. Keep doing this. It turns out that the number of lambda steps that we need is actually not too bad. It's only about n log square n. And what it comes to is, proving that my Markov chain with these weights actually mixes rapidly. And it uses a similar canonical path argument. Okay. But now I have to throw the weights in so things don't cancel out as beautifully as before. And I also want to point out that there's kind of 2 different weightings going on. There's the lambda weighting for the contribution of the matching itself, but then there is also the adjustment that I'm doing with the ratio so that I don't get this, remember the circular space that was kind of very different region sizes. I need to adjust with the current approximation of the weights so that I get the space kind of nicely partitioned into roughly equal size n squared plus 1 regions. Okay? So I think I kind of stop here. I'm not going to get into the analysis of the mixing time. But if you think about it, and so this is the result about of Jerome, Sinclair, and Vigora. There is an F-Proust for the permanent. And if you think about it, everything that I said about starting at the complete graph and computing the starting weights and fading away the edges, none of this really required a bipartite graph. I could have started with a complete non-bipartite graph. I could have computed the starting weights and so on and so forth. So the requirement for the bipartiteness comes from the analysis of the mixing time. Okay? And essentially it kind of boils down to if you take some alternating paths and I give you a guarantee on an edge, additional edge, if you have a bipartite graph, when you take 2 different alternating paths and connect them with edges, you're going to get an even length cycle that you can then beautifully decompose into 2 matchings. But if the graph is non-bipartite, you do not have this guarantee anymore, and that's where the analysis breaks down. So I'm just going to, very high level, leave it at that. So let me get to the last slide. So I guess the biggest open problem that I would dare to consider biggest open problem in the area is to figure out what to do for non-bipartite graphs. Thank you.
Questions? No. Okay, thanks again.